Good afternoon, everybody. We're going to start on panel 3. You'll find this very interesting. They find it very interesting already to see the speakers talking away. This panel will be on water management issues and industry best practices. I did want to let you know, not that you want to hear my sob story, but we got hacked on the naturalgas.colostate.edu website 3 days ago. So if you're having trouble getting into the website, you just need to refresh and try to go back. Those nasty hackers, but it's kind of messed up some of the links, so I do apologize, but it's back up. And if you're trying to get into the event app, be sure just to go down to the bottom if you've gotten an email and click on give me my credentials again or something like that, and it'll refresh your password and your username, I think. So this next topic is, like I said, water management issues. Ken Carlson, you're going to have to stop I feel like I'm in a class here. Ken Carlson is a professor of civil and environmental engineering, and he's the director of the Center for Energy Water Sustainability. Ken has been on our steering committee since the inception, and he gives us a hard time, I do know that, but he is a brilliant visionary when it comes to why we put on these symposiums, so I appreciate Ken's input for the past 5 years. Next will be Joe Lobato on industry best practices. He's a facilities engineer staff at WPX Energy. And as I mentioned before, we tried to pair an expert from CSU with an industry expert on these two topics. You'll have time for questions, and we do encourage that. And what you don't see is there's a big TV monitor, and it's counting down. And so they'll know when they've got to start wrapping it up for some questions, right, gentlemen? Right? Okay, so I'm going to start off with Ken Carlson. Please give him a warm round of applause. Oh, this is I think that's yours.
Thanks, Maury. Thanks for the introduction, which I'll remember, okay? So it does look a little like 24, the old show 24, you know, counting down. Let's see if I can get, okay, nope, whoops. So water management in unconventional oil and gas operations is what I'm going to try to give a sort of a broad view of. We've been involved with this here at CSU for about 5 years when really the oil and gas fracking took root and started accelerating in the DJ Basin was when we started to realize that we should bring some of our water expertise here at CSU to help solve some of these problems. So you can really break it down to water quantity and water quality, and we've looked at both in a lot of different studies. I won't talk about everything. When you consider water quality, I'd say you can break that down into two categories also, and there's of course contamination, which is maybe of greatest concern to the audience. Are oil and gas operations contaminating water? What is the probability? What is the risk? But the other part of it that I think is very valuable, and we're putting a lot of effort in, and Joe will talk about this, is reusing the water. A lot of the flowback, which is the early water, versus the produced water, which I think was discussed earlier. Rebecca talked about it, that it's produced in tandem with gas and oil. A lot of it is deep well injected right now, and so there's a pretty big push to not do that as much, to make beneficial use of the water, and I will talk about that. And of course, if we do that, that impacts quantity, right? If we can reuse some of the water, the oil field wastewater, then we don't need as much fresh water. I put this slide in here, and I'm not going to go through it in detail, but to remind everyone how interconnected things are. Energy, water, and agriculture is what we're doing here. But agriculture can also be food, right? So we have always needed energy to produce water. In fact, I think one of the facts up there is that 20% of the electricity, the energy used in California is for treating and transporting water. So, and you know, there's biofuels. There's a lot of linkages. So it's not as simple as just looking at water by itself and not including energy into that. And then recently, people have started to look at agriculture or food. I think Rebecca cited this earlier, and so she did some of the work for me, because maybe I have too many slides. Essentially, 0.1%, this was a study done by the Colorado the Colorado Water Conservation Board and the COGCC and another organization that's eluding me right now. But it says that 86% of the water is used for ag. You can look at this in different ways. The truth is, what it says is that 86% of the water is extracted is used for ag. Ag water is actually used multiple times, right? You irrigate, goes through the alluvium, someone else claims the water downstream. So it's not completely apples and apples here. And the other thing is, you have to take into account sort of local issues. You know, that if I'm the farmer that has lost or been outbid on water that I was expecting for some other use, that doesn't make me feel better that less than 0.1% is used for hydraulic fracturing. So, and I think Joe will talk about this too, is that it's still valuable. The water, I mean, it might be 0.1%, that's a number, but it's still a valuable resource, and a lot of effort's being put into reclaiming it, let's say. I think this was covered also by someone that this is actually the data we developed. We did this study about 3 or 4 years ago, published it, and it was because at the time there was this discussion about really, 5 million gallons a well. Well, if you get more energy out of that, if you have to use less water per million BTU of energy that you reclaim, then it's probably a better deal. In other words, it's a more efficient use of the water. And that's all I'll say, except I think someone else pointed it out, is by far the most inefficient use of water for energy is biofuels. So what constitutes water management? That's really what I'm going to discuss a little bit today. And this picture that might be difficult to see is an EPA drawing from several years ago. We've done a lot of work in this area, and we break it out a little differently. First, there's freshwater acquisition, storage, and transportation. And so acquisition, I think you understand. That could come from groundwater, that could come from cities, that could come from existing surface water rights. But storage and particularly transportation are really key aspects of the whole life cycle of water management. Frac fluid interaction with recycled water. So if we're going to recycle water, that's one potential beneficial use for it, is to let's use it to frack another well. Depending on the frac fluid you're using, it might or might not be compatible with that water. So a lot more understanding needs to go into that. Produced water management. So this is the water that's come back. You've got the same sort of thing. You need to collect it, you need to store it, and you need to store it safely. And I think one of the things you maybe got from the emissions, the air emissions section, was that this could be a source of VOCs. possibly methane, but more VOCs. Colorado has been pretty aggressive in trying to push for green completions or not using pits, not using open pits that would allow these volatile organic compounds to evaporate. But that's an important thing. And then transport. So I have this water at this pad. I've got to get rid of it. It's an E&P waste. I can't just dump it on the ground. So what are my options? Well, up until recently, it's been mostly trucking. And trucking's expensive. That's the good news, because that's driving industry to look for alternatives. But not only is trucking expensive, trucking is disruptive to the communities that a lot of this activity is going on in. If you've been in parts of Weld County, and things have slowed down a lot since the oil prices dropped, but let's say a year and a half ago, and you were in parts of Weld County, you'd be amazed at all these water trucks constantly going around, up to 1,000 truck trips per frac were possible. Okay, so road damage, diesel emissions, there's lots of things not to like about that. And like I said, the good news sort of is that it's a win for industry to get away from that. And I think it's a real win for the communities. Disposal or treatment, that's sort of the end. You're going to transport it somewhere, you're going to put it somewhere, or you're going to dispose of it so that it essentially is 10,000 feet in a formation that you probably will never use that water again. Or are we going to try to make beneficial use of it? And then recycled water management. So after you've taken it somewhere, let's say you choose the treatment option, that you've still got to figure out how you're going to get it to this place of beneficial use. And so you're back to the transportation problem. And if you throw trucking in, the costs go way up. And so it's really a logistics issue. And let me, I think this slide sort of represents that. I'm not going to go into this in detail, but this is some modeling that we've been doing over the last few years to try to isolate the individual variables that are important in this whole water management strategy. And so there's things like the quality of the fresh water, the volume of the fresh water, the transportation costs, and then what's the water quality needed for fracking? It goes through drilling and fracturing. We need to store it. We then either send it to disposal, or if we choose treatment, we need to know the volume that we're going to get. We need to be able to predict volumes. We need to be able to predict what the water quality is that's coming into our treatment facility. And then we have to decide what's the best beneficial use. Is it going to be an alternative surface use? And so what could that be? Well, that could be agriculture. That could be irrigation. That could be other industries that can use somewhat of an impaired water that are local. But when we run these models, the key is to minimize transportation, because I'm particularly trucking transportation, because that's where the cost is. So I like to do this as what would be best? If we could just go from where we are now to the ultimate solution, what would we like to see? Well, what we'd like to see is, we have an oil field here. It's producing water. We're collecting it in a tank. It's bermed. It's contained, so there aren't going to be spills. And then it's treated on site cost effectively. Has to be cost effective. And then there is a beneficial use for the water in the proximity of where the water was generated. And so in this sort of ideal picture, I would say that's, that it's maybe used for irrigation, or maybe used for, maybe put in a stream for downstream use. Now, we're not there, okay, but that is where I think a lot of people in industry I talk to are headed, and particularly with lower oil prices, this is it's a very cost-sensitive thing. So the challenge to engineers and researchers is to drive the cost down for the logistics of getting this kind of solution accomplished. And this is the same plot again, and we're talking, about some of these. I was going to mention the treatment box here. So leading into treatment, we need to know how much water is being produced. And I don't know whether everybody's aware of this, but this is a typical decline curve, or type curve is another term for it, of both oil and water, actually. And they don't necessarily have the same slope, but they have the same shape. And that means that wells fracked, opened up, 1,400 barrels a day. This is real data, I think from about 80 wells averaged together in a field of a local operator we were working with. And so day one, 1,400 barrels a day. By day 100, maybe 20 barrels a day. So that's one of the challenges that you're dealing with. If I have a fixed facility, a wastewater treatment plant, I pretty much know what the volumes are, and they're pretty constant. And plus, I have an infrastructure that's bringing the water to me, and all I have to worry about is the treatment facility itself. I don't have to worry about all the other logistics. And here's the other thing that makes this challenge even more difficult is the dispersed nature of the spatially dispersed nature of the wastewater source itself. So again, back to this domestic wastewater plant in Fort Collins or your city. There's infrastructure in place to bring the collection system, brings the wastewater to the treatment plant. The treatment plant's usually on a river or some other lake, or some other discharge point, so they don't need to transport it. All the effort goes into the treatment itself. This is a real development plan, which they become obsolete pretty quickly because of the changing conditions and prices, et cetera. But this shows over a 5-year period where the water would be needed, and it goes from about 150,000 barrels per well to 0. So there's a spatial challenge here in terms of this would be getting the water. If we're going to recycle it for fracking, this would be one of the challenges. But here's another way of looking at it is where's the water coming from? It's and again, this is actual development plan data from a few years ago, and this is how they were planning to develop the field. And so in this year, there would be a lot of water produced here, but not necessarily a lot of water demand there, right? The water demand might have been down here. And so, you got to, and how is it done right now? It's trucked. And again, trucking is expensive, and it's damaging to the community, et cetera. So this spatial logistics issue is pretty significant. How do we treat the water and then distribute it locally such that we don't have to incur many transportation costs? And so this plot shows what's sort of happening right now on the western slope, parts of Pennsylvania, well, really a lot of parts of the country. And what we did this to show two things. One is that even when things are going great, like here, and this was real data again too, I can't produce enough water to keep up with the wells I'm fracking. So even if I can use every drop of produced water, I can't, it's not gonna, and I can get it to all the wells that are gonna be fracked, I don't have enough. And in fact, it's about a 2.7 to 1 ratio. So in other words, I need fresh water, but this would lessen the demand. The other thing, though, that I was trying to point out is when the drilling stops, goes to zero, the water continues. Now, it is declining, but the water is still there. And this is what's, and I think Joe might talk about this a bit in the PONS, is that this is what's happening in several parts of the country where, drilling has slowed way down, but the water keeps coming. So what are we going to do with it? We can't use it for recycling. We can't recycle it for fracking, so we're going to have something else to do with it. All right, so quickly I'm going to go through some treatment process type concepts. You need to know what your quality is, right? And there's metals, there's BTEX, there's organic matter, there's stuff. It's not. I try to tell people that it's the naturally produced water is a pretty nasty thing. So let's say I don't frack a well. Let's say it's a conventional well. The water that comes back with the oil and gas, as I think Rebecca said earlier, is full of things like benzene, and you wouldn't be drinking it. So we start with the water being impaired, and then we decide we can, there's various levels of treatment. What level do we treat it to? Well, it really depends on what our target, let's say, use is. And I've put up 3 or 4 there. Probably the least amount of treatment would go towards if you're going to use it to frack another well. If you're going to use it for ag, maybe that's not quite as stringent as discharge. If you're discharging it to a water of the U.S., it's pretty stringent. And that controls the level of treatment that you're going to have to provide, and of course that controls the cost. And that last one there, which is salt removal, TDS reduction, is the most expensive. So that's sort of the tough one. And so you would be probably driven if we could, if we had this nice model like we're trying to develop that could predict all these things, it would give an operator, well, okay, I'm going to send this water today to this use because it allows me to treat it minimally and still beneficially reuse it. That's what we're trying to get at. So very quickly, there was a little bit of a discussion about gels versus not gels, and you use gels when you need the viscosity, but the gels create a tremendous amount of organic matter. So here we're looking at, we usually talk about slick water, which, as Rebecca described, is essentially just friction reduction. And the organic matter load is relatively low. If we go to a cross-linked gel, which a lot of operators in the DJ are using, and I think Anna Darko periodically does too, is what she said, so you're looking at a much higher viscosity, and this is real data that shows the difference. We actually had the opportunity to track the water quality for an operator near Denver that was doing slick water on one part of the pad and gel frac on the other part. And pH, alkalinity, conductivity, pretty close, but look at the difference. The organic matter, much less. So easier to treat. So the ability to recycle water is going to be dependent on the frac fluid that's used. Okay, I'm going to skip that because I see Maury getting up. And this I'm just trying to reemphasize the importance of understanding, the travel times, the well locations, the disposition of the water, what you're going to do with it, and it lends itself to a systems-type model pretty readily. So I want to get to groundwater contamination, though, for just the last 2 or 3 slides. We have done a fair amount with this, and I think it's been discussed. We see 3 mechanisms for groundwater contamination, one being surface activity. If it's an unconfined aquifer, meaning that there's no impermeable barrier between the surface and the aquifer, then it's subject to all surface activity. And that includes oil and gas, so potentially spills. Another is an actual casing breach, and that's what this would be. And so I think the whole idea of casing was covered pretty well. And then the third would be maybe an inadequate cement bond with the formation, or maybe with the casing itself, allowing stray gas from the formation to go all the way up into the aquifer. And so those are really the three mechanisms that we believe exist. And we've done some studies with COGCC, published a few papers on the presence in the Wattenberg. I'm not going to go through this because she did, but 3 layers of cement, 3 layers of steel casing. This I think is the last slide, and this was from a paper we published recently about methane contamination of groundwater in the Wattenberg and in the DJ Basin. And I guess the point I want to make here is, and the reason we did this was largely because the Flaming Faucet in Gasland was filmed in Fort Lupton, and there was a little bit of misunderstanding there on what was actually going on. It was biogenic methane, and biogenic methane has been present in the DJ for a very long time, and people have known that. And so we characterized how much methane there is and what the sources were. And the answer is yes, there is methane in the groundwater. There's coal seams underneath the Laramie Fox Hills aquifer, so that's not that surprising. But there were a few cases of thermogenic methane, meaning likely from an oil and gas operation. COGCC investigates those rigorously, tries to figure out what went wrong and seal the wells, etc. My own opinion is that they've been drilling in the Wattenberg for 40 plus years, and the casing requirements now are so much more stringent than they were even 10 years ago, particularly 20 years ago, 30 years ago, that when we do see this stray gas, it's likely from an older well, a legacy well. Can't prove that. So I'm going to turn it over to Joe, and hopefully didn't take up all the time. But.
Thank you, Ken. That was very good. There's not a lot of topics that I don't disagree with there. I think you're right on what you're describing, and I really appreciate the way you give us the parameters on how to think about produced water and the life cycle of it, and then in particular trucking. In my presentation, I'm going to talk about reducing trucking and that impact on the environment. So with that. So this kind of shows the cycle of water in the POS Basin. What I'm going to focus on is recycle, reuse, and reducing the impact on the environment. And it all starts with this, the cycle of water here. Looks like that battery's gone. So, starting with hydraulic fracturing, going on to completion of the wells. Flow back, water recycling, where you get your treatment and your storage, and then responsible resource development. So this slide gives you a good overview of the POS Basin. That's where I'm at. That's where I work, Western Colorado. That area. Okay, thank you. So this area in dark yellow is the acreage that we operate. This is truly a huge basin, 200 to 300 trillion cubic feet of natural gas. It's a long-term play. We hope that we're going to be there a long time, producing and developing. So with that in mind, we want to do it responsibly, want to be good neighbors, and want to do good things in the environment. So Ken talked about when things are rocking and rolling, you know, times are good. Right now, times aren't so good. We're down to one rig. When you're down to one rig, as Ken mentioned, you don't have, you have a lot of excess water. So I'm going to show you what we're doing with some of that excess water with injection and disposal. Typical fracking that we do is 50 to 20 stages per well, 3,000 to 15,000 barrels per stage. And on the proppant side, 100,000 to 200,000 barrels of proppant. And all that activity managing 880 million gallons of produced water yearly. So I'm going to jump to a slide here that shows some of our some results that we've had in one of our areas to the north. In that previous slide, this is our area to the north right here. It's called White River on the slide here, but we call that our Ryan Gulch area. So this slide shows some of the good things that we've done there. Between production, frac operations, frac flowback, and injection, we have moved and pumped through pipelines 3 million, almost 4 million barrels of water. And that equates to, because we're moving it through the pipeline, we've gotten rid of 33,000 truckloads of water. So in the POS Basin, you truck water for, if you got to truck it for a short distance, it's maybe $2 a barrel. If you're going to truck it a long distance, it's probably $5 a barrel. So you do the math there, it's a lot of money trucking costs. And that's the goal of water management and water infrastructure, is to try to manage that water in a more cost-effective manner, which leads to profitability. So, and that's the key, is along with all these good things, reducing recycling, less impact on the environment, we get the bonus of more efficient operation, and that leads to better profitability. And commodity prices where they are right now, that's real important. So once the areas of the natural gas producing area is defined, you want to step back and take a big picture look at the area you're going to be working with. So this slide shows an area of approximately 320 square miles, and you want to plan and build in stages. So when you take that big picture look, you want to build that infrastructure through and around the areas that you're going to develop. And that's what we're showing here. And infrastructure development on this scale doesn't happen in a short amount of time. You know, these are 2, 3, 4 year projects to build this kind of infrastructure and to build those facilities within that infrastructure. So also on this slide, you see a centralized water management facility, which I'll talk about in a little bit of detail later. So, you know, we can move that water around the loop and send it to that centralized facility for processing. On this slide, you also see a storage pit, which is, we have storage pits in our centralized facility, but also storage pits out in the field. These are temporary pits. In the centralized facility, they're more permanent pits. These pits will eventually be reclaimed and removed. Also shown on this slide is a centralized plan of development, so a CPOD. So, you know, as we develop, we'll put in these CPODs all around that water loop, and I'll talk about a CPOD here in the next slide. And all with the goal of efficient operations and water on demand for completions. So you don't want to have, you know, time is money. You don't want to have any waiting. This infrastructure allows us to deliver water on demand very efficiently. So this slide will give you an idea of what a CPOD is, centralized plan of development. So you can see on the upper right, we have 8 well pads that are planned. There's probably upwards of 20 or more wells on each pad. We have a centralized frac pad. So all of the hydraulic fracturing for these individual wells is going to take place from that centralized remote frac pad. So in the lower left, you can see the centralized frac pad here, and then the drilling operation in the background. Water is going to be delivered to that centralized frac pad from a water pit. So in that previous slide, we saw the water pit and how we can move that water from the pit to the centralized frac pad. We can also bring water from the centralized facility over to that frac pad. So much less impact on environment. I'm going to go forward one slide here. So here's the old way. The old way, we used to set up that centralized fracking operation on every well pad. Now we can take care of all the well pads in that area with one setup. So greatly reduces the footprint and the impact on the environment. And that's what you're after with responsible development. So here's another aerial view of a centralized plan of development. This view shows the centralized facility here, and then storage pit there for storing water and moving it over to the centralized frac pad. And then all the well pads in this area. So each one of these well pads has, up 20 wells or more per pad. And in this example, we're reaching out about 5,000 feet here, pumping water from that central location out to those well bores for the fracking operation. This slide kind of gives you an overview of what's going on in our drilling operation and fracking operation. So in the lower left, that represents an area of about 1 square mile, so that's a section. And you can see that you got well bores coming in from 3 different spots, basically. So here's a pad. Well bores are coming, from that point and that point and that point. So this is called directional drilling. Kind of use an S-curve to get out there to the target gas zone. And then in the POS Basin, we primarily do vertical drilling. This is an example of horizontal drilling. POS Basin primarily vertical. You can see all of our the gas producing zones, kind of little pockets there. We kind of give the analogies like a bowl of potato chips there, and we got to go through and find them all, and then as we pass through them, we go ahead and fracture them. In the last 2 or 3 years, we have started to get into the deeper Niobrara zone with horizontal drilling and fracturing techniques, but primarily the vertical completions in the POS. So Ken had an interesting slide showing the need for water, and when times are good, you don't have enough produced water to completely take care of your fracking operation. You're going to have to go out and get some fresh water. That's when times are good. So now, as I mentioned, we got 1 rig now in the POS, so we're in a water excess situation. So water disposal is something that's keeping us really busy. This slide shows times when we have excess water above and beyond our disposal capacity. So we'll have, let's just say we have 15 injection wells out there, limited capacity, and there's times when we have all of that injection capacity used up, and we actually, and the red shows times when we're going to have to be hauling water off for disposal. So that is the worst case scenario. You don't want to haul, because that's, we typically have to haul it to Utah from western Colorado. So $5 a barrel in that scenario there. So we got a little bit of work to do here in December, January, February 2016. And like Ken mentioned, it's real important to forecast. So, we can forecast all the way out. This shows us going all the way out to 2016. So this is an aerial view of that centralized water management facility. This is our Rulison facility, upgraded in 2009. This is an area of about 60 acres. All the processing, the initial processing is up here. And then one thing I wanted to point out on these facilities, we like to build them on a slope so that we can have gravity flow, so the water will flow through that facility on its own without pumping. That's an important step to remember, because we're trying to separate oil here. If you can avoid pumping, avoid mixing, if you can keep the water quiet, that helps your oil separation. So that's what we're doing there, building on a slope. Like I say, processing on this end and flowing through and into the storage ponds. This is our parachute facility, centralized facility, built, upgraded in 2012. So same thing, we're building on a slope here and flowing water down this way into our storage ponds. This facility has a covered storage pond. That's new technology, and technology that we use. You heard a lot about VOCs and VOC emissions. for a centralized processing facility, it's real important to, we have to operate under state permitted VOC emission limits on these storage ponds. So this covered pond allows us to bring in water that's not processed yet. So we can bring that unprocessed water and store it in that covered pond, and then our VOC emissions are handled with that pond cover. And then we can go ahead and process water from here, as needed and when we have time. So this gives us a big buffer to move water in and out, untreated water in and out, and then process it, at our own pace. And once again, all these facilities are, we capture all VOC emissions, so all these tanks have a closed process, no emissions. We use the infrared camera to verify that we're not don't have any vapor leaks. It is produced water, but I know one speaker mentioned it's mostly produced water, not too much VOC emissions. If you can get the oil out, there won't be any VOC emissions. But our produced water, we do have a lot of oil, a lot of condensate, and condensate that doesn't separate out in the initial process. It's more of a dissolved hydrocarbon that remains in the water, so you need further processing to get that dissolved out, and I'll talk about that. But it's that dissolve that'll get you on your VOC emissions, so you got to get that dissolved hydrocarbon out. I'll talk a little bit about that when I show the process. So just kind of an overview of the facilities. It's a major capital outlay for us, big commitment, $10 million easily between those two facilities. But it gives us the ability to have, facilities that operate within compliance. Emissions testing, we report quarterly to the state on those permit limits. They are state-of-the-art operations. I talked about gravity separation for the oil, getting that oil that'll separate immediately. Then you need a dissolved air flotation for a secondary treatment to get that dissolved out. And then we have oil emulsions treating, belt press, evap ponds. This pan here that big water pan, the one that's not you see ponds, and then there's a poly liner there. That's an evap pan. So we have a network of pipes running on top of that. We can spray water in there and get some evaporation going with that. So that's the evaporation portion there. We talked about fully enclosed for VOC emission. And once again, it's all about operating economically, cost effectively, and trying to keep profitable so you can keep operating. So these centralized facilities allow us to eliminate 100,000 truckloads per year. That's significant. So little overview of the process here. We talked about the skim tanks. That's just basically gravity separation. There is a little bit of engineering that goes into that tank. We have baffles and ways to prevent short circuiting of the water flow through there, give a little bit more retention time. But anyway, any oil that separates out there is skimmed off the top and sent over for storage and sales there. From the skim tank, we go into a surge tank or a polishing tank. That's primarily to give us a buffer so we can get constant flow. It's real important to have constant flow through the DAF, through that dissolved air flotation unit. So like I said, any hydrocarbons that don't separate in the skim tank are removed in that DAF. So you have a lot of dissolved, you have a lot of dirt particles with oil glommed onto those dirt particles, probably about the same specific gravity as the water, so they just kind of hang in there and kind of float and they don't come out. So you need chemicals in that DAF. So we use a coagulant and a polymer, basically set up a positive and a negative charge. The coagulant will set up a negative charge on those polymers, a negative charge on those particles, and then the polymer has a positive charge node on it that'll attract those particles. And from there we kind of float them to the top and then skim them off the top. So that skim that comes off the top is an emulsion. So we'll send it over the emulsions treating from there. We'll get another oil cut with heat and chemical breaker there, and send that oil to sales. And then any of the sludge that comes off that emulsion treating area is handled in a sludge management area with a belt press. So going back down to water coming out of the DAF. Water coming out of the DAF is now cleaned and it meets all state permitted limits for VOC emissions. From there, we're able to recycle, send it back out to the field for frac. Another thing we've been doing a lot of, especially in times where we have excess water, is sharing water with other operators. So, there are several operators in the area. We have more produced water than anybody. When they run out, we have plenty of water for them. And with our infrastructure, more times than not, we can get that water delivered pretty much to their pad and save them a lot of money, helps us out with disposal. So it's a win-win there. And then also clean water for injection disposal. So this is a slide that shows the storage ponds in these centralized facilities. We have no odors on those ponds, and that's because we have a real good pond biology, active pond biology that we encourage and try to grow in there. We do that mostly by adding a little bit of nutrient, primarily nitrogen. Then we use aeration. So with aeration, a little bit of nutrient, that pond biology is going to seek a food source. It's going to eat that remaining hydrocarbon out. There's probably 25 parts per million that's coming out of the DAF, that final DAF process, 25 parts per million going into the storage ponds. That pond biology will eat out that remaining 25%. When we go collect our samples and do our quarterly samples, we typically see non-detect for hydrocarbon in that water, which is that's impressive. That's hard to do, but when you do all the right things, you get there. And we've engineered out all the bad bacteria. A lot of times you get sulfur-reducing bacteria, and that's where you get that rotten egg smell, but we don't have any of that. So talk a little bit about the storage ponds out in the field. These are regulated also, permitted through the COGCC, CDPHE. There's also a migratory bird requirement requiring us to protect waterfowl, so we have nets that go around there. Once these pits are excavated out, you get that excavated area out. The first thing you do is you put down a Geonet layer. This thing drives me nuts. So we excavate out. Now you got exposed rocks and sharp rocks. So this material will go down, cover up all those sharp rocks, prevent any punctures on this layer. In between these two layers, you got just another mesh. It's called another Geonet mesh. Kind of gives you a little separation between those two layers. And then a second poly layer, which is a little bit thicker. We got 40 mil for the first layer and 60 mil for the second layer. We also put in a leak detection between these two layers. So we can go ahead and stick a probe or a device, a liquid sensing device in between those two layers. If you get any leaks coming through that first layer, that detector will pick up that leak. And if we see that, we'll be able to work it immediately and prevent any spills or anything going into the environment. I'll skip that slide. So we talked about sludge processing. This is our equipment for sludge processing. It's a belt press. This is a continuous feed process. Once you turn it on, you just keep putting the sludge to it until you're done. You compare that to the old method. The old method was a filter press, so it's kind of like an accordion type apparatus. You fill it up with sludge and you squeeze it. The problem with the old method was you had to add perlite. Perlite kind of helps that sludge collect and cake up, but the problem with that is you were adding more volume to the material, the waste material you had to handle. So the belt press doesn't use perlite, much more efficient process. And it's a continuous process versus a batch process. We're looking at about 80% decrease in cost over the previous methods. These next couple of slides just show some more facilities that are located remotely. And the takeaway here is just the automation on these facilities. We're able to monitor all of these remotely, monitoring pressures, flows. This picture lower right is an injection well. We have permitted pressures that we have to maintain, permitted pressures on those injection wells that we can't exceed, so we're able to monitor all that. We have high and low shutdowns. If we exceed pressure, we're going to shut down immediately. So that kind of speaks to the responsible operating methods that we use, able to shut down even if somebody's not there. That automated equipment will shut down. Kind of more of the same on these next couple of slides. This is a water transfer facility, remote facility. Everything's gravity fed into those tanks from the neighboring well pads, saving a lot of truck traffic and a lot of water haul cost there. And once again, fully automated with shutdowns. One last slide here on the automation. One of the things that we can do is monitor that flow and monitor the pressure. So we can measure all the flow going out of the facility and then also measure the flow going into the receiving facility. You can compare those two. If you have any differences, any anomalies, you know you got a problem. So that's an immediate shutdown. It gives us time to go out and check it out and see what the problem is. So I want to move on and talk about new technology. Ken talked about produced water and even though it is a small percentage, that's still valuable commodity. If we can clean that sufficiently and return it to the local hydrology, that's a goal we want to try to do. We continue to evaluate new technology. This slide here shows a test trader that we have on site right now evaluating a lime softening process. This is a process for surface discharge. It does use RO at the end, but for all you that know anything about RO, you got to really protect those membranes. So the real key to water processing and water treating surface discharge is the pretreatment. So we're spending a lot of time evaluating this lime softening process, ultrafiltration, chemical mixing of that lime, and then RO in the end. And as you can see, we've had some good results, and we're very proud of that. With that.
I know, Joe. I realize that Ken took some of your minutes, Joe, and you might have figured out that this is not Tyler. You are on time. This is not Tyler Bittner. Joe had to take his place at the last minute, so in your program it's been printed. But Joe, that was great. Please give him a hand. So much to share, so little time, right? And so there's just a couple of minutes now for some questions. Are there any here in the audience? It looks like there's one back there.
This is for Joe. I'm wondering the acreage of your facility that you showed us, how many acres that takes, and also your water line, the dimension of the water line. Is it above ground or is it trenched or any of those?
For the first question, those facilities are anywhere from 40 to 60 acres. The second question, we like to, well, I'm going to break it down into two pieces. You have the low pressure water lines for moving higher volumes, and then you have the high pressure frac lines, which are smaller diameter but higher pressure. So for the large volume water moves, low pressure, we like to put in 10-inch or bigger poly line. That gives us the ability to move 30 to 50 barrels a minute and give us that water on demand for completions. Also reduces the requirement for tank storage on that centralized frac facility. The more volume you can push to that centralized frac facility, the less tanks you need on site.
Are they above ground or below?
For our permanent facilities, they're all underground. And so we got about 42 inches for freeze protection out there. So we're about minimum 42 inches in the ground.
Looks like there's a question in the audience here. Thanks, Jeff. Jeff Ling, one of our senior policy advisors.
Hi, I have a question about the ponds. You said you optimized the microorganisms in the ponds. So do you seed a new pond from the microorganisms from a previous pond, or do you optimize at each site based on sort of the local parameters and so on?
Yeah, there's a lot of different approaches to pond biology. Basically, from a high-level perspective, that pond biology is going to find a way, and it's going to live on its own, regardless of what we do, and it's going to live based on the available food. So what we see is that pond biology will morph to the available food, and then we encourage that just by adding a little bit of nutrients, and then aeration. Now we do have programs where we've seeded, where we actually take several different containers and kind of seed it, kind of grow or starter batch of pond biology in those. I'm not sure that's necessary. I think that I can be just as successful with just a little bit of nutrient and then having that pond biology go after the available food in that pond. We use a lot of methanol in our field processes. We separate that methanol, keep it separate, but methanol is an ideal food, so you can actually use the methanol that we've separated as a food to kind of seed the ponds, like that as well. That's a really broad topic. and there's a lot to it. I like to keep it simple.
Great. Please give him a hand.